Hello everybody. It is exactly 11:30 right now, and I'm going to go ahead and give you your notes for tomorrow. I hope I'm not speaking too quietly. I might be speaking way too quietly though. Or actually I am speaking quietly right now and not shouting into the microphone because my wife and daughter are both asleep, and I just heard my daughter make some noises on this thing called a baby monitor, and that worries me a little bit, so I may have to pause the video at some point. So let's get going. Okay, this is for notes for Monday's class. In case you want to know why I'm not here, here are some reasons. Basically, you could sum it up as the joy of parenting. Kid was sick for all 4 days. Not really that fun. I wish I was there in class with you guys, though. Be able to ask you how you guys are doing, see what's going on in your fun and exciting lives, see how you guys look after the college deadline application has passed for many of you. So, yeah. Let's get going. And, sorry, 6th period. Okay, we are going to be on page 19 and 20 in your review packet, so make sure you have that out. We're going to be doing something called related rates, which you should have already seen the video for, so it should be somewhat familiar. And then once we're done here, you can go in and start working on these problems in class, as well as the extra practice problems in the back of your packet. Okay. Again, on this page, we are working on that one. Alright. I am tired. I may also fall asleep during the video, so if I do, somebody just shout at me, "Wake up!" Okay. Here we go. So here's a lighthouse problem. I think the video had it set up already, but just in case not, I'm going to go and do it anyway. So there's a lighthouse on a tiny island. So here's the tiny island. Tiny island, 3 kilometers south of a point P. Okay, so here's a tiny island. It's located south on a straight shoreline, because shorelines, of course, are always straight. Note the sarcasm there. And we'll call this point P. And we'll call this other one lighthouse. Okay, the lighthouse lamp rotates at 5 revolutions per minute. Now I need to assign a variable to this, and that's what I'm always going to... Oh, don't do that to me. Oh, no. Dang it. Okay, good. Got worried there for a second. Sometimes technology doesn't work well with me, and I have to end up going back and redoing parts, but I'm okay for right now. Okay, so there's a rate, 5 revolutions per minute. I should label that they got this value of 3 kilometers. And how fast is the illuminated spot on the shoreline moving along the shoreline when it's 6 kilometers from P? So let's go and graph the 6 kilometers part. The 6 kilometers part is going to be... and that will be 6 kilometers. So here's a point. And you'll notice here that we have this triangle. And this triangle is... and a zoop, and a doop-de-doop. Right there. So that's the triangle that we're looking at here. And this triangle will always be changing over and over again. This is all the information that I'm given. I do have one piece of information that I didn't use yet, and that's this lighthouse lamp rotates. This is going to be the rate of theta, because revolutions is how the angle is changing. So 5 revolutions per minute. Now remember, in each revolution though, so 1 revolution, there's always 2 pi. This is equal to 10 pi radians per minute. Oops, excuse me. Now you see me in my worst form, just burping all over the place. Ugh, it's embarrassing. Okay, so let's keep going here. So d theta dt is 10 pi radians per minute. We couldn't keep that in 5 revolutions because we want to see how much this thing is rotating around in one cycle, or in 1 cycle of minutes. And 1 minute, it's 10 pi radians. We're also going to need radians here because of trig. We're going to set some stuff up here with some trig. I should indicate that this is going to be a right angle. I don't know this actual distance, even though at their particular instant this distance is 6, it's not always going to be 6 because this point's going to move again and again and again as this lighthouse keeps rotating around. So this point 6 is there for that instance, but really this is x. And here's theta. And we could set up an equation now. Oh boy. We could set up an equation such as tangent theta. Why did I choose tangent? Because I have an opposite and an adjacent. So tangent theta is equal to x over 3. This is my equation. This is my equation for where the point is for any angle that the lighthouse, for wherever the lighthouse lamp is at any time t. Oh boy. Oh brother, this is not good. Okay. I'm going to see, since I want to know how fast, I'm going to need to take the derivative with respect to time. So I'm going to take the derivative here with respect to time. I'm going to take the derivative here with respect to time. And let's see what we get. I'm going to get secant squared theta, because that's what the derivative tangent is. But I have to do times the chain rule, because I'm taking the derivative of theta with respect to time. And because I'm taking the derivative of theta with respect to time, I have to put d theta dt equals. Please, for the love of all things that are holy, don't do a quotient rule here. This is going to be 1/3. And then since I took the derivative of x with respect to time, I have to put dx dt. I should have noted at the beginning, when it says how fast is the spot moving along the shoreline, moving along the shoreline, this little part here, is actually going to be what we're solving for. Oh, there's a crayon. Oh, my kid would love this. So moving along, oh, that's cool. Moving along the shoreline, that's going to actually be dx dt. And that's what we want to solve for. So let's go ahead and do d theta dt we know already. Let's get rid of this. So d theta dt was 10 pi secant square theta. And this is where your trick comes in. What is secant theta first of all? So I'm going to do some side work here. Secant theta is going to be hypotenuse over adjacent. Now the hypotenuse, when we have one side as 6 and the other is 3, I do Pythagorean theorem here, and I should get root 36 plus 9, 45. So my hypotenuse over adjacent is going to be 3, is root 45 over 3. Root 45 over 3. I'm worried about 36 plus 9. Okay, it is 45. Oh god, I was scaring myself for a second. Now secant squared theta is going to be equal to 45 over 9. I just square top and bottom whenever I square the secant theta, the fraction gets squared as well. So I get 45 over 9 equals 1/3 dx dt. And remember, dx dt is what I want to solve for. So if I multiply by 3 on the other side, I am getting 45 over 3 times 10 pi, which is really equal to 150 pi. Perfect, that's my answer. And the biggest thing that you guys could get out of this is, what does that answer actually mean? And what this means is the spot on the shoreline, so let's write this nice and neatly, Mr. Lakin. The spot on the shoreline, is increasing, because we have a positive first derivative, is increasing at 150 pi. Now, what are the units here? I have dx dt. dx, if I look back at my diagram, is for kilometers, so x is changing it with kilometers, and the time is per minute. So I have the spot of the shoreline on the shoreline is increasing at 150 pi kilometers per minute when the spot is 6 kilometers away from P. And I realize as I'm reading this that this looks horrible. So I shall read it to you one more time. The spot on the shoreline is increasing at 150 pi kilometers per minute when the spot is 6 kilometers away from P. This is a very long answer, and that's what that number actually means. So it's actually really, really important to understand what the relevance of this number means. And hopefully that was helpful, and we're going to go on to the next one. Here we go. A ladder is 10 meters long. Classic ladder problem. Okay, a ladder is 10 meters long. So a ladder, here's a ladder, 10 meters. The ladder never changes size. That's really important. Its top is slipping down a vertical wall because it always is slipping for some reason. While its base is being pulled away from the base of the wall at a speed of 0.25 meters per second. So the base right here is being pulled in this direction at 0.25 meters per second. I use that information. I use the top information, 10 meters long, got it. Along a vertical wall, check. Space is being pulled. How fast is the top of the ladder? So top of the ladder is going to be dy dt. That's what we want. We want dy dt when it is 6 meters above the base of the wall. So here's the 6 meters above. Now, this is a Pythagorean triplet, 6, 8, 10. But we also have to remember that there's a particular instant here. We don't always get that specific value, though, because as the ladder's falling, it's not going to stay right at 6 meters. It's going to stay, this value is going to change. So in parentheses, I'm going to put a little y. In parentheses, I'm going to put a little x. And let's make up a general equation for the position of where the horizontal and vertical position of the ladder is at any time t. And that equation would be Pythagorean theorem. X squared plus y squared equals 100 squared. I'm sorry, 100, not 100 squared, 10 squared. Now again, what this says is there's the position of the ladder for the base, there's a position of the ladder for the vertical part, for the top part, and no matter what those two values are, when I square them and add them, they should always equal the square of the ladder. Now all this is nice, but I need to see how this actually changes with respect to time, so I'm going to do a d dt, and d dt, bye-bye. I get equals 0 here. I'm going to get 2x dx dt plus 2y dy dt. Now let's fill in some values. 0.25 meters per second, that's how the x is changing. This is dx dt. And I have my x is 8. I have my y is 6. Now I just got to plug stuff in. I love this part. So I get 2 times 8 times dx dt is a quarter. 0.25, oh no. What happened? Okay. 1/4. Okay, 1/4 is 0.25 plus 2 times 6 times dy dt And when I do all this math, I get 4, I get 12, I think I get negative 1 over 3. And what this means is that when the ladder is falling, so when the ladder is slipping, but the ladder is 6 meters above the base of the wall, then that means that the top is going to be slipping at a rate of negative 1/3 meter per second. Now, the ladder is going to speed up as the ladder falls, so this value is going to change depending on the location of the ladder's top part. My final answer, though, how fast is the top of the ladder slipping? Negative 1/3 meter per second. Yes! Number 2. Each side of a square is increasing at a rate of 3 centimeters per second. Okay, let's see what we can do with this. Each side of a square. Let's get a square. Okay, check. Is increasing at a rate. So if I call this side x, then this little part is going to be dx dt equals 3 centimeters per second. I should have said this at the beginning. If you want to stop the video and try to start this on your own, you're more than welcome to. And then if you want to, resume afterwards, that's more than fine. That's all. Okay. But you can stop the video, try the problem on your own, and then check to see how you did afterwards. That's totally okay. Or you can just watch along. Your call. Okay. Now, how fast is the perimeter changing? Okay, so how fast is the perimeter changing? I'm going to assign a variable here. That's going to be dp dt. That's what I want to know. If I want dp dt, I need to know what the perimeter is. I need an equation for the perimeter. The perimeter is 4 times x. That's the perimeter for the square for any of length x. Which means that when I take the derivative with respect to time of both sides, so d dt and d dt, I can see that the rate that the perimeter is changing at is actually dependent on the rate that the side is changing at. And it's kind of noteworthy to mention. So I'm going to repeat that. When I take the derivative of the perimeter, I'm going to get the rate of change of perimeter. And what's interesting about that is that the rate of change of perimeter is going to be equal to directly related to how the length of the side is changing, which kind of makes intuitive sense in a way. So let's go and go dp dt is equal to, okay, the derivative of 4x is just 4, but I took the derivative of x with respect to time. And I know dx dt is 3. So that means that dp dt is equal to 4 times 3, which is equal to 12. And I always need to include units, so 12 centimeters per second. In other words, when the side of the square is increasing at a rate of 3 centimeters per second, the perimeter will also be increasing at a rate of 12 centimeters per second. Whoa! Zia, did you have a question? Okay, we can keep going. Mr. Virgil, do you have a question? I thought I saw a hand up. Okay. Last one. The cars driving toward an intersection is a very popular problem, so let's see what we can do with this one. There's a car heading east. East is this way. So here's east towards an intersection. Here's the intersection. The truck is heading south, away from the same intersection. Okay, so car heading east, got that information. At the rate of 40 miles per hour. Okay, so that means that if I call this x, I can say that dx dt is, wait for it, negative 40. What the heckaronies? Why is it negative? Okay, there's a great reason for why this is negative. My position in relation to the intersection is decreasing. And I'll repeat that again. The distance, anytime I'm along this line, the distance between me and this point is decreasing. And because my distance between me and the point is decreasing, my rate must be negative. So that's a negative 40 mph. Now a truck is heading south, away from the same intersection at a rate of 60. Here, the person's distance from the point is increasing. So if I call this variable y, dy dt is equal to a positive 60 miles per hour. At what rate is the distance between the car and the truck changing when the car is 8 miles from the intersection? Okay, so this is going to be 8, and the truck is 15 miles, and this is going to be 15. Okay, so 15, again, this is the y. Let me change what I did over here. Oh boy. Oh brother. Okay. 8, and this was x. Okay. So I got 8, 15. At what rate? So I got 8 miles, I got 15 miles. Now the distance between the two cars, that's going to be a variable that I'll always call z. And z is going to be this distance. Now you'll notice two things. One, the number is going to be 17. This is an 8, 15, 17 triangle. It's a right triangle. Number two, you may also notice that that here, unlike the ladder problem, I do need three variables. I need, because my car is changing position all the time, my truck is changing position all the time, which means this distance is never staying constant. In the ladder problem, even though my y is changing and my x is changing, the ladder never changes any kind of size. So there's no rate that the ladder could be changing. The ladder's position could change. Mr. Goldstein is awake. He just sent an email called "In Case Anyone Asks." I don't know what that means. Weird. Anyway, let's keep going here. So, I need all three variables for this one, and I'll set them up. I need an x squared plus a y squared equals z squared. And since I'm looking how this thing is taking place with respect to time, I'm going to take the derivative with respect to time on both sides of the equation. And I'm going to get equals 2x dx dt, and I'm almost done, guys. I know, I've been talking forever. 2y dy dt is equal to 2z dz dt. I'm sorry, I just burped. This is embarrassing. Okay, now I gotta plug in my values. 2 times 8 times dx dt was negative 40. Plus 2y, 2 times 15 times 60. Okay. And 2z is going to be 17 times, and we don't know what this value is because that's what we're trying to solve for. Yeah. Alright, and now, 2 times 17. Awkward. Okay, that's a moot point because I'm going to divide everything by 2, and I'm now left with negative 320 plus 15 times 6. Oh, it's 900, I think. Oh, please, right. Is equal to 17 times dz dt. This is a 900, I think. Okay, so that's going to be 580 equal over 17 plus dz dt. And 580 divided by 17, my handy calculator is going to tell me that that's a number. 80 divided by 17. Oh, 34. Okay, and again, even though this is the answer, what I'm going to strongly encourage you, I'm checking 15 times 60, I don't trust myself. It's too late and I make mistakes at this late. Okay, I'm right. Oh, thank goodness. So even though it doesn't ask for it here, what the meaning is, I'm going to say it, and you're welcome to write it down, and I'll repeat it. What this answer means is that at the instant the car is 8 miles from the intersection, the truck is 15 miles from the intersection, the rate that the distance is changing between them is decreasing. So, I'm sorry, the distance between them is increasing, rather, at 34 miles per hour. So I should really restate this because I botched that up. When the car is 8 miles per hour away from the... I'm sorry. Oh my goodness, I'm going to bed. When the car is 8 miles from the intersection, traveling at 40 miles per hour towards the intersection, and the truck is 15 miles away from the intersection, traveling at 60 miles an hour away from the intersection, the distance between the car and the truck is increasing at 34 miles per hour at that particular instant. If you want to hear that again, just rewind. And other than that, guys, as obviously I need to go to bed, so good night.